Possibility of non-azeotropic mixtures. For the systems of air conditioning and refrigeration, non-azeotropic miscible mixtures are often used as the working fluids alternative to the discontinued ones. However, these fluids have a well-known unavoidable disadvantage of heat transfer deterioration resulting from the increased interfacial temperature due to the existence of mass diffusion resistance. At the same time, for the non-azeotropic miscible mixtures, there is an unknown effect of Marangoni force exerted mainly by the concentration difference along the liquid-vapor interface as a result of the preferential evaporation of more volatile component. In aqueous solutions of alcohol with a large carbon number, the surface tension is increased with increasing temperature depending on the range of concentration and the level of temperature. In such a condition, Marangoni force due to the concentration gradient is enhanced by also the temperature gradient along the interface, especially near the three-phase interline extended at the base of bubbles. The enhancement of critical heat flux, CHF, was shown by Vogten-Petre and Van Stralen based on the experiments using a wire heater. Abe verified the drastic increase of maximum heat transportation for heat pipes using self-rewetting mixtures. Sakai et al. Confirmed the small enhancement of heat transfer in the ranges of very low alcohol concentration in water, while no appreciable increase in CHF for a flat heating surface facing upwards. As a consequence, non-azeotropic mixtures have no advantage from the viewpoint of the improvement of heat transfer. Expected performance of immiscible mixtures. Innovative cooling systems which meet the requirement for the increased heat generation density from electronic devices are urgently required. To enhance the values of CHF for the cooling of a large area at high heat flux larger than 200 W/cm2 as shown in Figure 1, the present authors confirm the validity of the device structure which reduces the effective heating length by the liquid supply directly to the downstream of the heating duct from the transverse direction. An example of the structure is illustrated in Figure 2. However, such structure is rather complicated. On the other hand, to ensure the high reliability for a long-term operation, microstructures on the enhanced surface cannot be accepted depending on their application. The present authors notice the superior heat transfer characteristics in nucleate boiling of immiscible mixtures even on a smooth surface, Kobayashi et al., Onishi et al., Kita et al., which are summarized as follows. The value of critical heat flux is increased by the self-sustained subcooling of less volatile liquid as a result of the excessive compression by the high partial vapor pressure of more volatile component. The operation at a pressure higher than the atmospheric is possible keeping low liquid temperature to prevent the mixing of incondensable air which seriously deteriorates the heat transfer in the condensation process, i.e., a final heat dissipation process, due to the existence of mass diffusion resistance. The surface temperature is decreased during the free convection or nucleate boiling of less volatile liquid, which is caused by the substantial heat transfer enhancement by the existence of vapor bubbles generated from the more volatile component. The excessive overshooting of the surface temperature at the initiation of boiling can be reduced by the selection of more volatile component and the optimization of its distribution on the heating surface, which is required, for example, for the cooling of automobile power controllers with a large fluctuation of thermal load. Difference in the size and heat flux level of semiconductors as a target of cooling. Device structure of cold plate for the cooling by flow boiling in a narrow channel.